I'm going to be talking about interactive random matrix theory in Julia. I put HTML and PDF versions of my slide up if you want to scan it, and I'll give you a couple of seconds. Oh, yeah. So who am I? I'm Simeon. I'm currently writing my master's thesis with Alan Edelman and Dirk Hundertmark at KIT Karlsruhe. I've been involved in the Julia community since 2019, and I'm mainly interested in computational mathematics, language design, automatic differentiation, and
Simeon,
compilers.
Please don't look behind you when you talk, because the mic is in front of you. So look at the slides on your screen if you can.
I have them in front of me.
Thanks.
Yeah. So what I'm going to be talking about is the determinantal point processes. And I want to convince you that they are a really powerful tool in random matrix theory. And I think Julia can really bring these to life. Why do we even care about determinantal point processes? Well, one really big application right now is applying them for machine learning. For example, you have, you see here, these different pictures of Porsches, Philadelphia, or Cocker Spaniel. And what you want to do, you want a diverse set of recommendations. And so you want to enforce diversity, but at the same time, you also want quality. So they have to correspond to the right words. And this is what they use for in machine learning. But I think they also have they also come up in some really fascinating pure mathematics, and that's what I'm mainly going to be talking about today. So what are determinantal point processes? I said they're a really powerful tool. So the core concept is that a point process is a random subset of 1 through n. And what I really want to emphasize here is that the random variable is a subset. It's not just a number, but it's a subset of 1 through n. For example, if you have n equals 1, you might think, oh, there's just one possibility. But no, there are two. You have the empty set and you have 1, which are both subsets of the set of 1. And for example, for n equals 2, you then have 4 possibilities. You have the empty set, you have the set of 1, the set of 2, and the set of 1 and 2. And it scales with 2 to the power of n. So for n equals 4, you would have 16 possibilities. And what's special about these probabilities is they're based on determinants of an n by n matrix. And this is almost always denoted by k. And what is special about you can the special source is if you sum up outer products of orthogonal polynomial kernels. You can do that up to a degree k, and that will result in a really special DPP called a k-DPP, which will always give you a subset of a length n, or of length k. So I really think DPPs are important. You don't need to understand the whole concept to get my talk, but I really quickly just wanted to give you an overview of what DPPs are. And I really think the DPPs harness the power of statistics, combinatorics, and linear algebra in a really neat way. I want to start with an example of such a determinantal point process. And we're going to start with growth from a corner. So you have to see this corner on the left, and you have one possible square. The squares always need to be supported from left and from below. So at each time step, you then flip a coin, and for each possible new location, so each location that would be supported by a square from the left and from below, you flip a new coin, and you keep it if it's heads. You drop it if it's not not heads, and you repeat that over and over again. So these rules sound fairly simple, right? What happens if we do this many times? And this is a really interesting fact. it turns out the boundary tends more and more towards a circle, and this is already quite interesting. No, you can even generalize this to arbitrary coin flip possibilities, so the probabilities of choosing a nude square to be filled. And for those kinds, it's actually an ellipse. I will show you this later. And I think this really emphasizes it, that simple rules can lead to some fascinating asymptotic phenomena. So, for example, we see here, I have put this interactive demo in Makie together, and we can skip forward a bit. So now we have a square here. We have two possible new locations. For each of those, we flip a coin. And oh, yeah, shucks, we didn't choose one of those. But now, in this step, we chose them. So now we get more squares. And we can scale it up till we fill the whole area. And what I told you earlier is that we can do this for large n. And for large n, we see this nice circular shape. Or if we modify p, we even see like an elliptical shape. So what does this all have to do with random matrices? Well, let's zoom in a bit and look at the deviations from the circle. So you have this growth from the corner, you have this circle or ellipse, and you now zoom in and look at how does this deviate from this? How does the frontier deviate from the circle? And it turns out it gives this distribution. I histogram the deviations, and this distribution looks almost like a Gaussian, but we are going to be talking a lot more about this distribution in particular. But why it's interesting, I think I still need to convince some of you. And now we're going to be talking about something seemingly completely different, namely random matrices, and in particular eigenvalues of random matrices. So the question I pose unto you is basically, what if we have a random Hermitian matrix? So in Julia, we can just generate this with the rand_n command. And we look at the eigenvalues of this random Hermitian matrix. This is a problem that was first described by Eugene Wigner, who was like a really famous physicist and a Nobel Prize winner. And he was actually studying quantum mechanics when he encountered this problem. So at first, you would ask, like, what does this have to do with corner growth at all? And it turns out, again, we see some kind of circle. If you look at the eigenvalue density, you draw up a histogram of those eigenvalues, you see that it tends more and more towards a semicircle for large n. We still need a couple of steps till we are at random growth. And in particular, now we're going to be looking at the largest eigenvalue. So in this histogram, just at the very right, at x equals 2, we're looking at just the largest eigenvalue. We're going to be doing this a bunch of times, and Julia makes this really easy with this eigmax command, and we're going to be histogramming this as well. And already we see, yeah, that some of you might recognize it from previous slides. Namely, it lines up with the distribution of those deviations from corner growth. And I think that's really something fascinating. Like, we looked at these completely different processes, and suddenly, like, the same distribution appears. And this distribution in particular is named after Craig Tracy and Harold Ridham, two mathematicians from the US. And I'm going to say it's basically the Gaussian of random matrix theory. It basically appears everywhere you look, and every process you study eventually turns out you encounter this Tracy rhythm distribution. So why use Julia for this? So I think Julia has a couple of advantages that make it really suitable for these kinds of problems. It has an interactive environment. It really enables research as well as teaching. Those notebooks have been used for teaching in a classroom. You can really get in touch with the problems and really dig down. And it has the performance necessary for these high-dimensional simulations, which is quite important because you notice you sometimes have to make n quite large to see those interesting statistics you actually want to see. And it also has a great scientific community. And I would even argue it's literally designed for random matrix theory. If you look at the first paper, Julia, A Fresh Approach to Numerical Computing, one of the very first things they do is they calculate eigenvalues of a random matrix. So now I'm going to be talking about a different process that turns out will have connections again to those previous two processes. I'm going to be talking about Aztec diamonds. The name might be kind of a misnomer because it's not just the Aztecs that had these patterns in their art, but this design can actually be found in a lot of pre-Columbian art. And what you do is you have this diamond shape, and you basically lay over a checkerboard pattern over this, and then you divide it into domino tiles. So each tile covers exactly 2 squares, and if you do this, you look at random assortments of these squares, and you encounter 4 different ways those those domino tiles can lay on top of the checkerboard. Namely, you have 2 horizontal ones, one with a with a white square on the left, one with a gray square on the left, and you have also 2 vertical ones. Those are the different types that are possible. And if you do this, you can color these domino tiles in the respective colors, so for the 4 different types. And you already see something here, that namely that the same types seem to bunch up in the corners. This is something we're going to be looking a bit more at in some time. But this is already quite interesting, I think. There is, so now we're going to be looking at random assortments of these domino tiles. And there's an algorithm called the shuffling algorithm, which is really quite interesting. And it's known to produce uniformly random tilings. There's basically just 3 steps to this algorithm. You first remove, you add these arrows to the tiles, which point in a particular direction. Namely, in the corners, they all seem to point outwards. And you remove dominoes where these arrows, they face each other. Then you move dominoes in the direction of their arrows. And then it turns out the empty the empty space left behind can be filled exactly by squares. And you can fill this by either 2 horizontal or 2 vertical dominoes, depending again on a coin toss. And I think it's really, what I want to emphasize is that this complex combinatorial problem, which is at first might seem quite intractable because there are so many possible combinations, it reduces down to a really quite scalable and even parallelizable algorithm. And what is the now I want to demonstrate this on my laptop. I'm loading the Aztec Diamond package, which I published, as well as the AMD GPU package here. And what we can just do is we can first just generate a 10 by 10, an order 10 diamond on the CPU. But what I can now also do is I can generate diamonds on the GPU. So this is actually all written in Julia, It uses its own, it uses AMD GPU.jl, and it parallelizes this shuffling algorithm in a way that's really suitable for GPUs. And you can see it finished this 2000 diamond quite fast. And if we view it, it's going to take 1 second. Yeah, I know, Julia latency. And there, we see a large diamond. And what's also already quite interesting is that you can see there's a circular pattern going on. I'm going to be talking a bit more about this in a couple of seconds. But first, I want to ask again, what is the random matrix connection of all of this? And it gets a little in the weeds, but you can draw zigzag paths in between the domino tiles. And you see here these red bumps. So you can just draw a straight zigzag through them. You sometimes have to do a right down step instead of a down right step. And I've marked those in red. And it turns out that there are exactly R bumps in each diagonal. So the top diagonal has 1 bump to the right, the second has 2 bumps to the right, and so on. And this is actually a DPP again. So if you sample, you can sample the location of those bumps through a DPP. For example, here, the first one would be a set containing just 4. The second one would be a set containing 4 and 7, and so on. And those are actually the K-DPPs I talked about before. And again, this K-matrix can be constructed from outer products of discrete Krautchuk polynomials. I won't go into too many details, but again, we see here that something really interesting happens if you construct a K-matrix from orthogonal polynomials. Besides the zigzag paths, you also have these DR paths. This is where you step up if you encounter a red square, you step right if you encounter a blue square, and you step down if you encounter a green square. And you can do this for multiple starting positions. And what we are mainly going to be looking at is the top DR path. And this top DR path has the property that it will evolve into approach a circle for large enough n. So does it really approach a circle? We can ask that question, and I ran a simulation on my computer. On this tiny laptop GPU, I was able to simulate a diamond of order n equals 10,000, which is really quite a lot if you imagine it's basically a 20,000 by 20,000 array. And you can see it's really approaching a circle where there's chaos in the middle, but all the edges line up perfectly. And if you were to zoom into this, we could zoom in here. You can see it's really just dominoes all the way down. So now I want to talk a little bit about what I'm currently researching and what's caught my attention in particular right now is that there are other kinds of tilings. And namely, there are tilings of rhombi. Here it's a hexagon. And it turns out you can tile a hexagon by rhombi, and it has some very similar properties to the Aztec diamond. And basically, you have the correspondence of these tilings to non-intersecting paths, which is also quite interesting. And from those non-intersecting paths comes the DPP connection. And if you look at the pattern on the right, it almost looks like a cube filled with smaller cubes projected down to 2D. So there's this something I'm interested in, I study random tilings and the statistics of those. And it turns out very similar to the Aztec diamonds. The same rhombi bunch up again in the corners. And you have this inner circle where again it's basically chaos in there. You can also even generalize this to other two n-gons. So for example, octagons. Here we have a 6 by 6 by 6 by 6 octagon. And you can again tile this by different rhombi. And it again matches up perfectly and covers the space. And you have statistics, but it turns out these are quite a lot more difficult to generate, because there are no known shuffling algorithms or similar for those. So you have this combinatorical problem. You can kind of approach it by starting out with a regular pattern and then doing these flips, but it's really not known how to do this that efficiently. So that's what I'm studying right now. And what I think is quite an interesting figure is this one, where I can start out with a hexagon, and then I draw these slicing paths through the hexagon, and by that you can generate octagon tilings. And this is an approach I'm working on right now. It's using Julia, and it's I'm even running some of it on the GPU, and I hope to do research this way and perhaps discover something new about those tilings. So in conclusion, I really think computation can enable new insight in mathematics and really build intuition. And I think Julia is at a really special place here, because its performance opens up new possibility, but it's still all within an interactive environment. So you're not like in C, where you have to compile after every step, but you can have these notebooks, you can have the REPL, you can play around with code. And I think that's really an advantage in these types of scenario. And I think my ending message is that many phenomena in mathematics could be simulated, but aren't. Like theoretical mathematics often focuses on the theory, but it rarely actually runs those simulations and puts them into code. And I think that really can really open up new insights. And even if not, I think it's really useful for teaching. And so I think there are lots of opportunities for these kinds of problems out there. And I encourage you to give it a try yourself. Try out my packages, write your own packages. I think there's really a lot there to tackle. And with that, I thank you for your attention.
Thank you very much. A very fascinating talk about these tilings. I'm interested in, I know about the sort of physics interpretation of random matrix theory, where random matrices often resemble, systems that display quantum chaos, and then their physicists like to look at level repulsion, so at the repulsion of eigenvalues of these random matrices, depending on which can be different strength depending on the symmetries of the matrices. Mm-hmm. Is there any connection to random tilings, or any interpretation in terms of these level repulsions to your tilings?
I honestly, I'm not quite sure about the connection between these. So I mean, there's lots of connections going on to those random ensembles and polynomial ensembles, but I don't know of any connection in particular to the repulsion you are talking about.
Okay, yeah, no, thanks.
In the back.
Thank you for this very nice talk. I enjoyed a lot the math and also the the figures, and I was wondering whether you had to pull some tricks to display so many dominoes, or was it like very straightforward? Do you do it on GPU directly, things like this?
Those dominoes, I actually for the Aztec diamonds, this is just generated using images.jl. So you just have these, every domino is basically 2 pixels, and you fill those pixels, and this way you can generate quite large images really fast. For these kinds of figures, I have used Makie.jl, which is really convenient for this interactive stuff and drawing in paths and all this goodies, and it can even be interactive inside a notebook. Does that answer your question?
Yeah. I'm asking myself if these techniques can be used in combinatorics as, for example, I don't know, enumeration problems or proof. Even in combinatorics, use this kind of tiling to do some of this stuff. Do you have ideas on this?
So, sorry, I did guess the question.
Okay. I wanted to ask if these techniques can be used in combinatorics to do some enumeration or stuff like this, or are they not applied in this case?
Yeah. So I would argue they are already combinatorical questions.
Okay, yeah, indeed.
Combinatorical problems, right? Because and there are some interesting combinatorics, in particular about the Aztec diamonds, where you can use combinatorics to count how many tilings they are. You can there are even some connections with like Young diagrams and these DPPs. So there are a lot of connections. I couldn't mention them all in my talk. But yeah, there's definitely something in common there.
Thank you.